session. I'm now going to demonstrate you guys for the KMPk set A, question number 3 for the year 2022 and 2023. So let's start. So natural fluoride FnO2 is very chemically reactive. The fluorine and oxygen atoms are bonded to the nitrogen atom. So it's hinted here that the nitrogen atom is the central atom. Take note on that. So the first question, draw the most palatable Lewis structure for FnO2 molecule. So as I said from the previous video, to determine the Lewis structure, you must first calculate the total valence electron. So nitrogen has 5 valence electron times 1, because from the molecule there's only 1, so 5 times 1, so 5 times 1 is 5. And next for F, in the molecule there's 1, so F fluorine has 7 valence electron, so 7 times 1 is 7. And O has 6 valence electron, and from the molecule he has 2 atoms, so 6 times 2 is 12. So 5 plus 7 plus 12 is 24. So you should draw it first. So O, single bond N, single bond O, single bond F. F. And then since there's 24 here, 1 2 3 4 5 6, 1 2 3 4 5 6, 2 3 4 5 6. So now we need to recheck it. So if you can see, this one is already octet, the oxygen is already octet, the fluorine is already octet, and this oxygen is already octet, but the nitrogen is still not octet yet, it's still not stable. So in order to stabilize it, we need to move one of the lone pairs to the middle, like this. So when it's moved to the middle, it should be double bond. So N, single bond, double bond O, F, 1 2 3 4 5 6, O, 1 2 3 4 5 6. So one of the lone pair is removed, so it's gone. So 1 2 3 4. So now we can recheck. 2 4 6 8, 2 4 6 8, 2 4 6 8, and the nitrogen is 2 4 6 8. That means all of it is now stable. Hence, this is the most possible structure. So, and then we need to calculate the formal charges. Just like in the previous video, in order to calculate the formal charge, it is Fc is equals to the valence electron minus the bonding pair minus lone pairs. I'm going to show you guys one example, and you guys can calculate the rest. So we're going to take the O. So O has 6 valence electron, right? And the bonding pair, which is the line, bonding pair is the line, and the lone pair is the dots. So bonding pair, which is the line, has 1. So 1 is 1. The lone pair, which is the dots, is 1 2 3 4 5 6. So 1 2 3 4 5 6. So it has 6. So 6 minus 1 minus 6, that means C is equals to -1. Hence the formal charge is -1. And it's the same for the other ones. You calculate the formal charges. So for the next question is draw the molecular geometry of FnO2 molecule and name the molecular shape. So when the question asks something that's really related to molecular geometry, you need to list all of the required information, which is first to determine the class. And how to determine the class is by looking at this. So A is the central atom, central. The B is the terminal. Okay, so the central atom, which is N, has 1, so A is 1. This terminal is B, so there's 1, 2, 3 terminals, so that means AB3. So the class is AB3. Now for the rest, there's no other way of doing this except that you have to remember or memorize it. So once you draw the Lewis structure, the molecular shape, it should be looking like this. Okay, and the bond angle is 120. The electron pair arrangement is trigonal planar. The molecular shape, it does not change anything, so it's still trigonal planar. And then, so number 2, moving on to the next one, is predict the polarity of FNO2 molecule. So to determine the polarity, you know, it is related to the electronegativity. As you can see, O is more electronegative than N, and F is also more electronegative than N. Hence, it is attracted towards the nitrogen is attracted towards them. And F is more electronegative than O, and then both of the O's. So that means the dipole moment should be going upwards, and the mu does not equal to 0. Hence, the written is FNO2 is a polar molecule because fluorine is more electronegative than nitrogen and oxygen. See, just like I said earlier, which is an uneven distribution of charge. The dipole moments does not cancel each other out due to the asymmetrical shape. Hence, the dipole moment does not equal to 0. Next on, the fourth question. Using the orbital diagram, describe the hybridization of center atom. So it's already told you to describe the center atom of FNO2 molecule. And to describe, that means in each of the state that you have to describe what is happening in the state. So the center atom we determine is N. So N from the valence electron, since it is N plus, that means it has given 1 electron, right? So originally from here, nitrogen is 2s2 and 2p3, but since it has given 1 electron, it should be 2s2 and 2p2 only, because one of the electron is given away, hence making it N plus. We know it's an N plus is from the formal charge. So N plus 2s2, put in the valence electron. This is the ground state. So there are only 2 unpaired electrons. However, 4 unpaired electrons are needed for formation of 3 pi bonds, 3 sigma and 1 pi bonds. Then so that means you have to move one of these. So we need to promote one of the electrons to the front in order to excite the state. Just like this. So N plus into this. So 1 electron from a 2s is excited to an empty orbital into p, hence forming an 4 unpaired electron. Just like you see. See here, this is 2 unpaired. There's 2 unpaired electrons. What it means by unpaired electron is this. There's no pairs here. This one is already paired, but this one is not. So there's 2 unpaired electrons. But to form the hybrid, which is the sp2, we need to excite. We need to move it to 4 unpaired electrons. See, the 4 unpaired electron is needed for formation of 3 sigma and 1 pi bond. So that's why we move it to the front. See, we excite the state. And then this one, which is the hybrid state. So this is sp2, and this is the hybridized orbital, and this is the unhybridized orbital. So 1 2s orbital and 2 2s orbital are hybridized into sp orbital. See, it's got 1 2s orbital and 2 2po. That should be 2p, by the way. I'm sorry. This is 2p. So 1 2s orbital and 2 2p orbital are hybridized into sp2 orbital. So 3 unpaired electrons are ready for 3 pi bonds, and 1 unpaired electron in the unhybridized orbital is for formation of 1 pi bond. That is how you describe it. So moving on to the next question, the boiling point of diethyl ether and 1 butanol are 34.5 degrees and 117 degrees respectively. Both compounds have the same molar mass. Explain the difference in the boiling point. As you can see here, one butanol has a way higher boiling point than diethyl. That is because from their structure, for diethyl ester, there are no, as you can see, there are no OH group or hydroxide group here. So that means they cannot form hydrogen bond with other molecules. But butanol has, as you can see here, has a OH group, which is a hydroxide group, which enables it to to form a strong hydrogen bond with other molecules. So one butanol and has OH groups and can form strong hydrogen with other molecules, while that latter lacks OH group. Hence, it can only form big dipole forces between molecules. Hydrogen bond is stronger than dipole forces. Thus, more energy is required to break the bond. Therefore, one butanol has a higher boiling point than diethyl ester. Okay, so let's move on to our last question. Q has the following properties. Q can behave as an insulator at low temperature and as conductors at high temperature. Q has also comparatively narrow energy gap between the valence bond and the conduction band. Based on the properties given, what is Q? Give an example of Q. So it's quite obvious from this first clue what is pointing out here. It says it can behave as an insulator at low temperature and as conductor at high temperature. So we already know, at this point we already know that it's a semiconductor, right? But if you want to further prove that it is a semiconductor, then let's look at the second one. Q has a comparatively narrow energy gap between the valence bond and the conduction band. So what is narrow energy gap? So basically we are talking about the band theory here. So for metals, right? For metals, there are no gaps between the there are no gaps between the valence bond and the conduction band. Actually, it also overlaps. So that means electrons can jump easily from the conduction band to the valence. It can jump, so electrons can jump easily between the conduction band and the valence band. This is for the metals. And for semiconductors, there are actually a small gap here. So it can still jumps, but it's not as efficient as a metal. But for insulators, it has a very large gap. So when it has a large gap, electrons cannot travel from there to here. So it is proven that since it is comparatively narrow energy gap, it is proven that this is a semiconductor. So Q is a semiconductor. And for example, and there are a few examples of semiconductors, but I choose silicon. There are mainly like 4 semiconductors that we should learn. Silicon, there's also germanium, gallium arsenide, gallium arsenide, or 3 arsenide. But of course the easiest to remember is silicon, hence why I put silicon there. So that is it for today. Thank you guys for watching, and I'll see you guys in the next video.